Going into our notes, a couple things I have filled in already, some of our definitions. This chapter is, I won't say heavy on definitions, but it does have a lot of terms, 6 specific new terms that the kids need to learn. And the first one is a relation. A relation is a set of ordered pairs. And during class, we played around with the idea of, maybe coming up with a way to remember the definition better. So your student can talk to other classmates or even come up with something themselves. Sometimes we have riddles or phrases or just words that relate, like for example relation. You could think about that as a relationship, and ordered pairs, a set of ordered pairs maybe being like a pair, like a couple that would be in a relationship, things like that. So they can come up with, if they'd like, a more unique way to remember that the definition for a relation is a set of ordered pairs. So now let's take that idea of a set of ordered pairs and show how you can represent it in multiple ways. It's a big thing in Unit 2, Chapter 4, is using multiple representations of data. So we have some ordered pairs here, and we're going to take these ordered pairs and we're going to write them as a table, as a graph, and as a mapping. The students are familiar with table and graph. That's pretty easy. Mapping is a new topic. So if we create a table, basically a table would be an X and a Y table, and so if we use our ordered pairs, we're just basically splitting them up into their X values and their Y values. The X values for this set would be 3, 4, 5, and 0, and then the corresponding Y values would be 2, 1, 6, and 7. Likewise, we could graph that set of ordered pairs, that relation, on a X and Y axis. Here's your X, and here's your Y. I'm not drawing that big enough. We'll see in a minute. And if we map our ordered pairs, if we draw them out, graph them, you've got 3 and 2, which would be here. Remember, the X term goes first, the Y is second. 4 and 1 would be right here. 5 and 6, let's see, we've got 2, 3, 4, 5, and 6 would be up there. And then 0, 7 would be all the way up on the Y-axis, up here on 7. So all of those are representations of the relation, the set of ordered pairs, 3, 2, 4, 1, 5, 6, and 0, 7. Now, a mapping is very similar to a table. A mapping requires that you draw 2 kind of rounded rectangular boxes. You can make them big ovals if you want to. It's not really important how you draw them, it's just that you get them done correctly. And in the first rectangle, I'm going to put the X values, which are 3, 4, 5, and 0, and then the corresponding Y's, 2, 1, 6, 7, and you use arrows to map, so to speak, these values to each other. So the 3 would go with the 2, 4 with 1, 5 and 6, and 0 and 7. This is a pretty easy mapping. Sometimes you'll have repeated values in a mapping, and so the arrows can get a little bit more confusing, but this one's pretty straightforward. They just all go together. So that's 4 different relation examples of the relation of how to make a relation. Our next 2 values go hand in hand with this. The X values, the set of X values is our domain, and the set of Y values is our range. So we'll really get to where we talk about domain and range quite a bit. Instead of saying what the X values are and the Y values, we'll call those domain and range. And again, I've provided an area if you'd like to come up with a different way to remember domain and range. You're welcome to do that in those boxes. All right, let's practice. Let's actually list and write out what the domain and range are for each of these situations. Writing the domain and range for a table, for a set of ordered pairs, and a mapping is quite simple. You're just literally listing out the values. So for example, on number 1, if I'm going to list the domain, you put a big capital D and then a colon. That basically says the domain is. And then we're going to list out the values, which in this case would be -2, -1, 0, and 1. Those are our domains. And then your range would be 4, 1, 0, and 4. It's as easy as that. For each problem, you're just simply listing the domain and range. You do that for a table. You do that for a set of ordered pairs. So this one would be 4, -2, -5. The range would be 5, 6, and 12. Mapping number 3, again listing your domain, would be 0, 1, 2, and 3. The range would be 8, 7, 6, and 5. And for mapping number 4, not harder necessarily, but you do have to consider that the -4 right here does go with 2 range values. So when you list it, -3, -4. Need to make sure you list that -4 twice because it is used 2 times, and that'll be important later when we talk about functions. And the range for this one would be 10, 11, 12, and 13. Now, a little bit more challenging is writing the domain and range for a graph. And so what we'll see here, you need to think about the domain as being the width of your picture, so to speak. So if I'm looking for the domain of this particular value, we're going to write it like a compound inequality. A compound inequality, just as a reminder to the students, in the past we've had an x in the center. We have symbols, this one reading greater than or equal to because you're reading it out from the center. This one being less than or equal to, and so when you look at them, they both look like less than or equal to symbols. And then whatever value you might have in the problem is on the outside. So that's how you list your domain and range for a graph, but the domain is going to be with respect to the width of the picture. The range is going to be with respect to the height. So let's see how that works. For this one, I'm going to have the domain is, we know domain is x, so I write it in the center. I've got my left-facing symbols, which in this case would be greater than, equal to, less than equal to, reading it from the center. So I'm going to look at the width of this picture. I notice that it starts over here at -2, and it ends over here at +2. That shows how wide that line goes with respect to the x-axis. So that is its domain, -2 to +2. If we think about how tall it is, for example, the picture starts down here at +1 and it ends up here at +4. So the range is y, and again, symbols facing the same way. It goes from 1 to 4. So a little bit more challenging to write your domain and range for a graph, but we've done compound inequalities before, so hopefully that'll be kind of a carryover from Unit 1. Now, our picture didn't show up very well for some reason, so let me draw this little guy in. There's actually a rectangle, and I think during class I did different rectangles for each class period, so if you have one different than some of your friends do, that's fine. So we're looking for the domain and the range for this particular picture. Domain, remember, is the width. So if I look on here, I see that my picture starts out over here with a width of -3. Domain is x, remember, and it stops over here at +2. That's how wide it is. So that's its domain, -3 to +2. And then if we look at how tall it is, so to speak, starting on the y-axis, it starts at 1. Remember, range is y, and it ends up here on top at, let's see, 1, 2, 3, +3. So that would be the range. So there's different ways of stating the domain and range. Mainly you're going to be just listing them out, but it is possible when you have a graph that you write them more in compound inequality form. All right. Another definition, and a function is a big definition for this section, for this unit. A function is a relation in which each domain value is paired with exactly one range value. I've never been a huge fan of this definition, although it's pretty common sense. It spells it out, but I like to think, to me, the way to remember a function is almost to remember what a function isn't. If you can understand what to look for in the domain and range, then you can tell pretty easily what a function is and what a function is not. So in conjunction with this definition, I like to use the idea of thinking about if there is a repeat in the domain, then the relation is not a function. That's basically what we're looking for, is repeated values in the domain. If there is a repeat, then we do not have a function. If there's not a repeat, then we do have a function. So it's kind of a case of opposites. All right, so let's look at some examples here. On the left, I have examples of things that are functions. For example, this table right here, do you notice in the domain how there's no repeating values? Then that means it's a function. Now notice we did have a range repeat. That doesn't matter. We don't look at the range at all. We just simply look at the domain. In this graph, if I was to list out all the ordered pairs and look at the domain for this would be 2, and that would be 3, that would be 4, that would be 5. Again, just listing out the ordered pairs. The x values, there's no repeat there, so that's a function. Likewise, on this mapping, no repeats. The 2, the 7, the 8, and the 15 go to, each are all unique. Now, notice the 2 and the 7 both go to the 4, so that would mean the 4 would repeat in the range, but when we're thinking about functions, we only look at the domain. Now, over here on the right, we have examples of everything that would not be a function. See the repeat? that table would not be a function because there's a repeat in the domain. Likewise, if I was to list out the domain and range for this graph, notice how both those dots line up on top of each other. They both would have a domain value of 3. That would be a repeat, so again, not a function. And then on our mapping down here, notice how the 6 goes to the 7 and the 10. That would be a repeat in the domain, therefore those would not be a function. So finally, let's look at these 3 and see if we can tell whether they're functions or not. If I'm looking at the table, I'm always focusing on the domain, and I notice I have a repeat in my -3's. So it says tell whether the relation is a function. This would be no, not a function. And the reason why is because there is a repeat in the domain. And I'm going to write domain like this. Number 8, that one looks great. It does have a repeat in the range, but we're just concerned about the domain for functions. So this guy would be a yes, he's a function, and the reason, no repeat in the domain. Now finally, pictures, as we saw above when we had the dots on the graph and the ordered pairs lined up or didn't line up, we're going to learn something new for graphs, and this will be the last thing we'll do in our notes. It's called the vertical line test. Great little test to see if a picture is a function or not. So basically what it means is if you draw a vertical line anywhere on this graph, if the vertical line touches the picture in more than one spot on any place on the graph, then that means that it is not a function. You basically don't want your vertical line to touch the picture twice anywhere. So for example, if I draw a little vertical line over here on the edge of my triangle, notice how it just touched it once? That's cool. I could even do that over here on this side. See how it only touches it once? How great is that? But if I draw a vertical line right down the center, see what happened? It touched there and there. That means that this is not a function. If I was to list out all the ordered pairs of this triangle, I would definitely see a repeat in my domain. But sometimes the pictures are going to be pretty extensive and you wouldn't want to have to list all the ordered pairs. So this is a nice little test to see if something is a function. This one is not, and the reason is because it fails the vertical line test. So let me give you just a few more little graphs to look at. Like for example, if I have a picture of a graph and I just had a linear function, just a line that's just straight. If I draw a vertical line anywhere on this picture, do you notice how it only touches once? That would be a yes. That is a function because it passes the vertical line test. Even if I had a graph maybe perhaps that was curved, one like this, which is called a parabola. We'll learn this second semester. But anywhere on this line, if I draw a vertical, it only touches it once. So this guy would be a yes also. He's a function. That's good because it only touches one time. What if I took that idea of a U-shaped graph, a parabola, and I curved it this way? The first time I draw a line, see how it touches twice? So that would be a no. That means that's not a function because it fails the vertical line test. So anytime you have a graph, you can use the vertical line test to test it. Ooh, that was lots of information. You may need to watch this one more than once, but we'll be working on this unit for 2 weeks, and it's pretty easy information. So I think once you learn the new terms and be able to relate them to the practices that we did in these notes, I think you'll be just fine.